Good morning and good afternoon and good evening and welcome to the Friday Talk Show with Global Electronics and with your host Rajiv Kulkarni. Right now the time is 9 a.m. Central Standard Time of USA, based in Dallas, Texas, and 7:30 p.m. Right now it's Indian Standard Time. So Global Electronics brings you every Friday different topics on electronics manufacturing, whether it's design related or whether it's process related, quality related, or market intelligence, the supply chain challengings, logistic, and so on and so forth. As we know that electronics industries are growing exponentially, and the technology is advancing more and more. The circuit design gets denser and denser, so the power handling capacity starts increasing, so the thermal management solution becomes very important, and so forth. There is a very domino effect or a ripple effect on the electronics design as we advance in our technology. So today's topic, we are talking about physics based HSIO interface design, which is a part 4 of the episode or the series, I would say. And the title is Differences Between Central Office and Hyperscaler Systems. The synopsis goes like this: both telecom central offices, that is CO, and hyperscaler systems utilize the concepts of racks and backplanes. But their engineering priorities, physical specification, and logical functions are fundamentally different. The core difference lies in their operational focus. Telecommunication equipment is designed for high reliability, long life cycles, and managing hundreds of thousands of slow, deterministic data streams. Hyperscale, in other words, AI backend systems are designed for raw parallel throughput, massive power density, and extremely low latency communication across a small number of massive nodes. Ladies and gentlemen, let's discuss this topic, very advanced topic, I would say. And we have the technology expert with more than 4 decades of experience in the design side of it, the PCB design, or also he is engaged in the DFX, DFM activities for more than 4 decades in the electronics industries. Mr. Ambaprasad, who is based out in Silicon Valley of India, Bangalore city, which is a southern city, southern part of India. So, Mr. Ambaprasad, good evening and welcome to you. How are you this evening?
Oh, doing very good. Uh,
Excellent.
yeah, you told it is a new topic. It is not new. 40 years back, central office was the leading edge.
Uh-huh.
Now it is a little sort of stabilized. And now hyperscalers since past 5 years are in the focus. So
Yeah,
it is, it's,
that's what I said. That, ladies and gentlemen, Mr. Amba Prasad carries a wealth of experience, wealth of knowledge in this particular field, and as mentioned, he goes way back 4 decades, and that's how he knows that this is not a new topic. This is something which existed before, and but we are. I would say this is a more of implementation to the current technology. What do you think, Amba?
exactly.
Okay. Okay. So let's move on to our presentation mode, and I will start sharing the screen here, and then we'll move further on this. Okay, so here we go. I will go to the presentation and I will enhance the screen. Okay, are you able to see my screen?
Go to the next page. Okay, you can stay. You can go to one previous page. Doesn't matter. Yeah, go
Yeah,
back.
that's what I thought because we spoke about HSIO interface channels. So, yeah. Okay.
So we started covering high-speed I/O channel design and implementation about 3 weeks back, 1 month and some 3 episodes. And we started discussing primarily on the PCB part of it and like that. And suddenly some of the people called and told that why don't we go at a system level, and the decisions are taken at a system level. Let's go back and defend from the system level. That's why I pedaled backwards. And this week we are starting at a system level. Maybe down the line we go at a rack level and PCB level and things like that. So anyway, go to next page. This is where we stopped. We told if we don't verify things, especially the simulation results and layout recommendations and design envelope, if we don't verify, it becomes a reverse analogy here. A sheep wearing a wolf's clothes, a very
Close.
small, tiny issues will suddenly get blown up, and it's very difficult to tame them. This is where we stopped. This topic we continue little maybe in next episode onwards, but this episode let's pedal back, relax a bit, and then start at a system level. Go to next page, please. I have told physics-based interface routing, system-level interfaces, differences between central office and hyperscaler server rack. Okay, next page.
Yeah.
This is the agenda. Both the telecom central office and AI backend systems utilize the same concepts of rack and sub-racks and backplanes. Mostly nowadays it has become a rack. But their engineering priorities, physical specification, physical realization, and functional partitioning are fundamentally different. We compare the two racks, we compare the backplanes, and we got a functional summary. And the retrofitting of central offices as well as the new hyperscaler racks, they depend heavily on optical transceivers. So that's why I thought a couple of slides on optical transceivers. And we talk about some power efficiency, the roadmap, etc. Then we go forward. Then we go to a PCB level, maybe next episode onwards. Go to next page, please. This is a AI generated image. I took a lot of effort in keying the wordings for that. It shows the key difference between a central office on the left side, telecommunication central office system, where it disaggregates all sub-modules. What in our company previously we called as a central module and a base module. 32 base modules we used to aggregate with one central module. That used to do the core switching. The same architecture may differ from company to company, but the concept is the same. There will be a telecom rack and there will be line cards, switch fabric, and power modules, then protection, grounding. Then generally people used parallel bus almost up to 1990. After 1990, people went towards a serial bus. That is nowadays a serial bus is taken for granted. Whenever we say high speed IO, we are talking basically of a serial bus. And again, and on the other side, we have AI backend system, which is called as a hyperscaler server rack. This use high power and cooling. And then focus on extreme throughput and latency, very high power density. In fact, the power density is so high, sometimes the entire rack can be a power rack. So it's like that. Again, liquid cooling is an option. Air cooling is no more possible. But here, central office is built for, I mean, whatever we designed 40 years back is still serving the market. That's how it is. But AI backend systems, they get upgraded every 3 or 4 years. But design is little future ready. I can't say future proof, but it is future ready. You don't need a forklift replacement. It can be upgraded. Next page, please. So same as usual, the picture what I have shown, made a table here, primary goal, rack standards and form factor. Primary goal, central office reliability and integration. Uh, Host modular cards with guaranteed uptime and long service life. Redundancy is built in. Then we have generally 19-inch rack. EAA is the standard. There is a standard company. Generally, it is called as a telco, the telco for telecom operator. So not our
Okay.
Indian telco. This is telecom operator. Okay. And whenever I say telco, people thought how many vehicles you are selling per month. So telco is a telecom operator. So
Right.
okay. Then very deep 600 millimeter to 1000 millimeter depth, but can be shorter also. But usually the height is 42 U. 1 U is 1.7 inch. So that's
Okay.
the height. And then there will be a floor layout, ironwork, cabinets, etc. Hyperscaler throughput and power density provide unprecedented power and cooling to maximize GPU computational output. Often custom and semi-custom are adhering to open compute project. This is the equivalent to UAA. This is the open source OCP standards. They have written a lot of standards. And certain companies can even go beyond the standard. They may establish their own ecosystem. NVIDIA is one such. They are building their own ecosystem. But people follow either this or that. But sometimes if something becomes very popular, OCP takes over and standardizes it. That's how the ecosystem is working. Go to next page, please.
The rack is the
Again,
physical
this
framework.
slide
Yeah.
I've just slightly focused power density 2 kilowatt to 10 kilowatt per rack. Traditionally, 48 volts based power distribution. Air cooling, still air cooling is applied, relying on natural or hybrid airflow from cold or hot aisles, designed to run indefinitely for controlled environment. 20 to 25 year PLM life cycle. I told even 40 years back what you have designed, they are still there. If I go to any remote part of India, I see those systems, they are there. Even
Yeah.
I saw a few of them in Calcutta last week when I was there.
Wow.
Hyperscalers, extreme 40 kilowatt to 120 kilowatt per rack. Uh, you see the difference now. It is almost 100 times. High density requires a medium voltage feed, 400 volts, or even people are using 800 volts sometimes, direct to the rack through bus bars, and you convert within. First, liquid cooling, mandated for densities above 35 kilowatt. Air cooling hits the physical threshold. Liquid loops are required to manage high-end heat flux from multiple GPUs and CPUs, and generally the industry call XPU and something PU. Like a CEO, CTO, we call CPU, GPU, XPU. So that is a generic name we give. Week 2 months for a new iterations, 3 to 5 years for depreciated life cycle. Performance obsession drives rapid turnover. When I show you the roadmap up to 2050, I'm showing a roadmap, you'll be amazed. This is the key difference. Next slide, please. Now here we are covering backplanes. Again, on the backplane, we'll be having a separate episode, but I'm just, this is some sort of a curtain riser. Primary goal, aggregated reliability, cross-connect hundreds of line cards to a central switch fabric without a single point of failure. Typically, passive backplanes consisting of almost entirely of traces of a very high density connectors. Example, advanced telecom say, architecture, VPX. VPX is 50-year-old. It's still working.
Wow.
Uh, they connect line cards, interfaces to switch fabric cards through backplane and cables. Here, hyperscaler system, extreme intranode throughput, intranode. In fact, hyperscalers, they use at the backend. They are the sellers, they are the customers. Interconnect the GPUs to each other to the main system bus at a maximum bandwidth. Highly integrated, often proprietary GPU baseboards like NVIDIA baseboard. They must handle the most demanding PCB challenges such as 20 plus layers. This is my field. 20 layers plus 20 layers. Today is like a what a 6 layer was say 20 years back. So if you say multi-layer, when it came 4 to 6 layer, it revolutionized. But
Yeah,
now 20 layers we have to use here, and a very tight impedance control.
I know that for a reason that multi-layer boards, when we were selling, 4 layers was a big deal at that point of time. And now, you know, the layer of have increased so much, up to 84 layers I've heard. People have some demand on the 84 layers boards.
I have seen a
Anyways,
120 layer board for a load board, semiconductor testing board. I have seen a cross section. It is,
wow, wow,
yeah.
yeah,
So here
okay,
we can take a break. It is exactly 7:45. We are halfway through.
okay.
We are halfway through
We
here
will
also.
we will do that, and I'll stop sharing the screen here. So, ladies and gentlemen, let's watch this quick video, and we'll be right back. Good morning, good afternoon, good evening, and welcome back to the Global Electronics Friday Talk Show with your host Rajiv Kulkarni. So, Global Electronics brings you every week different topics on electronics manufacturing activities, whether it can be related to process engineering, quality, the testing, or the design aspect of it, which is DFX, DFM, and so on and so forth. So, Mr. Ambaprasad is a technology expert, have been in the industry for more than 4 decades now, and he's also currently the president of SMTA India chapter, which is the Surface Mount Technology Association India chapter. He brings wealth of his experience in the design sector, and Global Electronics' main object is to share the wealth of experience among the electronics community, which can help for the young engineers in process or in design or so on and so forth. So let's continue our next second half session of today's show, and here we go. Yep.
Next page. Go
One
to full
second.
size. That double arrow.
Yes.
Next page.
Comparison. Yeah, yeah. I already did.
Oh, signal
It's
type.
on.
Yeah, we are there.
Yeah. Yeah.
So our entire the series was supposed to be the signaling type. That's what we were about to discuss. But again, we went back towards a system level, and we took a little deviation. We pedaled backwards, and we are going forward now. Signal type manages in a central office, manages a mix of signals, low speed control signaling, power distribution, and aggregated user data streams. Example, 40 gigahertz and 100 gigahertz Ethernet lines. Bandwidth focus, aggregated throughput, hundreds of parallel deterministic lines, example 100G Ethernet channels that are switched centrally. Hot swapping is very much important because of redundancy. Every line card and fabric card must be hot swappable. That means you have to replace the card when the system is live. You cannot shut down the system to do that. It's hot swappable. For example, if you go to Bangalore, any Shell petrol bunk, when you are filling petrol, they say switch off the vehicle because
Yes.
they accidentally the ignition can the petrol bunk can catch fire. That's what they say. Or
Yeah.
maybe I think The secondary goal is people should not be with the engine on. They should not just start and run away without paying money. I think that is the primary goal. Anyway, I'm not able to decode that. Anyway, but here, hard swapping means you should be able to replace the cards with the system is live. It can be any card. All cards are hard swappable. Every line card and fabric card must be hard swappable to maintain 5 nines of availability, 99.999% uptime. That's very crucial. Uh, in a hyperscaler backend system, nearly pure, uniform, high bandwidth data lines. Example, these are all proprietary. Some of them are multi-source agreements. Some of them are proprietary. For example, NVLink is NVIDIA uses that. InfiniBand, PCIe Gen 5, 6, 7 is already available. PCIe 7 is available, 8 is under the works. Focus is entirely on movement between compute and memory. That is a major traffic is between GPU and memory. That's it. Point-to-point raw bandwidth interconnection of 8 GPUs to act as one. Each GPU needing 900 GB per second to 1.8 TB per second of a throughput. Secondary usually managed at a high node and a whole rack level rather than individual card level during the active training job. The AI, we know AI training, you know what it means. So this is the key differences, but there are still other differences are there. Next page, please. Functionality summary. Again, this can be a base unit or a optical line system. Connect millions of subscribers with a guaranteed low error service indefinitely. This is the primary focus. Data plane, millions of independent, relatively slow streams. Example, voice call, data session. Control plane, vital and distinct. Example, signaling for call setup, security. Still, the military uses this. They are because of the security issues. They use central offices. They're not gone. They are still available. Uh, Aggregating many standard interfaces, T1, E1, or Ethernet into a highly reliable, redundant fabric. AI backend system again, train a model with trillions of parameters as fast as possible. Massive synchronous memory copies to all reductions across 8 GPUs, often integrated with GPUs and specialized switches. NV switch, this is again from NVIDIA, managing their own communication fabric. Proprietary custom design to provide maximum direct memory access between a small number of massive chips. And here, the difference is central office is still telecom, big daddies. They are there everywhere. Sometimes some of them are government companies. Many telecom companies are government owned, at least in the third world. But here, the hyperscalers is mango economy. Mango, what is mango economy? Some people know that. Maybe next session we can tell what is mango economy. Uh,
Yes.
Maybe people can do some Google search and find out. This is generally mango economies are controlling this hyperscalers. Next page, please. Again, this central office, this is just a picture how they look different. This is just a cartoon. This is not the actual engineering drawing. Minus 48 volts DC power. Here we use a plus 48 or plus 12. Why plus? Uh, because they were using the 12 volts earlier, plus 12, they went to plus 48. But in telecom, they generally use minus 48 volts. Air cooling front to back, hot air in and cool air in and hot air out through a aisle. 19-inch HCR and NEPS approved rack. Patch panels and fiber trays in cables will run very long distance to the fiber room. Here most of them are some of them are active, some of them are passive cables. Hyperscaler rack plus 48 plus 12 volts DC power through bus bars, liquid and immersion cooling, 21-inch OCP rack. OCP is another standard company. High density cabling, many times intelligent cabling, rear door heat exchanger, liquid cooling, and cables, optical cables. Optical cables are always there. Next page, please.
The
Engineering
engineering
takeaways.
takeaways. Yeah.
Uh, uh, Central office racks prioritize robustness and service continuity, often constrained by a legacy power and cooling systems. Backward compatibility is a must. DCI racks push signal integrity and thermal limits, demanding advanced PCB material, optical packaging, and rack level power conversion. Traditional transitioning from central office to data center backend design involves redefining rack level signal integrity, power integrity budgets, fiber topology, and thermal envelopes. Central office rack, the two picture comparison, this I have told already. Again, same thing I have just printed over here. Hyperscaler plus 48 volts or plus DC bus, liquid cooling loops and a rare and heat exchanger. Now all AI systems are liquid cooled. The air cooling is out. They are at the almost at the out of air cooling mechanism. Next page, please. I mentioned earlier, without optical cabling, these hyperscalers would not have been possible. Some couple of slides on co-package optics evolution. Pluggable optics data rate growth and energy efficiency 2000 to 2025 are captured. In year 2000, 10 Gbps, 2005, 2005 again, 2000 10 Gbps, 2005 10 Gbps, 2010 40 to 100 Gbps, 2015 400 Gbps, 2020 1.8 Tbps, 2025 1.6 Tbps. These are all the MSA standards. Basically, they measure one is data rate, other one joules per bit. How many joules we are using to transport a bit. Actually, here I captured joules, but people talk about a picojoule. They have mentioned very clearly approximately how many, it's very clear. It's almost 2 Tbps we are talking about, and we are using almost 0.04 joules to transport on bit. It cannot go beyond that. Nothing works at zero. That we should realize. Next page.
Your voice is going little low, so
Now,
now it's better. Yeah.
same thing happened to me when yesterday I attended some webinar.
Okay.
Okay.
Yeah.
Anyway, I will explain again.
Yeah.
One slide back, please. 2 Tbps, we are almost there. 0.04 PJ per bit, 0.04 joules per bit. That's the rate we have did. It cannot go to zero. This will remain there for some time to come.
Okay.
Next page, please. This is just a roadmap.
CPU
This is
evolution roadmap.
neither to
Yeah.
scare someone or not to appreciate somebody. This is purely hypothetical. This is based on the proprietary search engine what we have. In fact, I used Max also to generate this, SMTA Max to do this. 2026 to 2030, 800G is going to be the mainstay, 1.6 terabit. 2020, this is consolidation and ramp up. Every evolution, there will be a revolution and then an evolution.
Yes.
We say we are in 6G now. 1G,
Yes.
2G, 3G, 4G, 5G, 6G. Each G will be, 1G will be a revolution, then it will be evolution. In evolution, you consolidate. 800G, 800G is almost today, that is the currency. 2031 to 35 terabit era, 1.6 T, 3.2 T. 2036 to 2040 multi-terabit expansion. 2041 to 2045 optical electrical convergence. That's it. It will converge. 2046 nobody knows. It is beyond the pluggable. At least I will not be here. I can be there up to this. I'll be there up to 2036. I'll be active. I'm sure about that.
Okay. Let's hope everything goes well for everybody.
But what our predictions we have given here, it can realize 5 years before. Every time, whenever they projected something on optical, it was realized 5 years before. What we say 2026 to 2030, it may happen by 2028 itself. What we say 2035 can happen at 2030 itself. So with that hope, I'm telling by 2036 itself, what we are seeing here will get pushed back here.
That is true
This is
because
possible.
the technology is advancement. If we look the pace they are going, right? The technology is advancing at such a fast pace. You never know how soon these can even come. So
And
yeah.
second row, QSFP DD, QSFP, these are all MSAs, service agreements. OSFP is Octa, QSFP is Quad. Uh, Onboard optics, chiplet integrating into chiplets, embedded photonics, use case, AI and ML hyperscale. It can be, they are projecting something. Still, it is AI and ML hyperscale only. Then thermal challenges, PCI Gen 8 224 Gbps signaling, that is going to be a challenge by 2030. Quantum data centers, already some companies are working on it, even in Bangalore. Exascale computing, optical fabrics, photonics co-design. There is no end for this. This keeps everybody engaged.
Okay, so the next one.
Next one.
I think we are done.
Oh, we are done. This
Yeah.
is the one. No, you
Okay.
put that. Go to the next
Okay.
page. Keep it. Here, let me explain this. This is generally we end with one slide, which is going to be a curtain raiser for the next episode. In 2012, one book was written on how to do high-speed layouts by Ralph Morrison. He's a good Motorola veteran. He wrote a book called as Mac 1 gigahertz. What he
Okay.
mentioned is to do 1 gigahertz sort of a data transfer on a PCB. The challenge is like building one Concorde plane. His book is named as Mac 1 gigahertz. He told 1 gigahertz is the cutoff. If to do 1 gigahertz in 2012, the amount of parametrics, engineering, precision required is like designing a Concorde aircraft. That time it was a marvel. Now same logic extrapolated. He wrote one book in 2012, and 2017 he wrote another book. In fact, that was the last book he wrote. He stopped writing,
Oh.
and 2 years back he left this world. Okay, but
Oh.
nowadays the people still use his book. A very good book. It is hardly 150 pages, but it makes a very good reading. Every person who wants to do high speed signaling should read that book. Here we are comparing side by side the engineering challenges which went to make a Concorde. The same challenges are required, side by side comparison I have given. But this we unravel in the next episode. In my next
Yes.
episode, we'll be seeing a lot of Concorde photos and corresponding
Okay.
PCB technology photos.
Okay. Let's do that next Friday then.
Yeah, we can do it, no problem.
Yeah. 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 Okay. Sounds great.
So please ask your people to request for questions, or if they want something, they can let us know
Yes.
what they want to
So
address.
yes, I already put in the YouTube our comment section. So people, the audience, you can put your questions at a later stage also. We will visit your questions, and if there are any, then we would address that in our next episode for sure. And in the meanwhile, please take care of yourself as we bring every Friday a new episode with the new topic as it is needed for the electronics manufacturing. And Mr. Ambaprasad has been a great contributor so far in our channel. If you have any specific questions, if you have any specific topic that you think that we need to bring, will be definitely happy to bring that for you and address that in this show. With that said, thank you very much, Mr. Ambaprasad. We will see you again next Friday with a new topic. And thank you all, the audience, for watching our show. And please do contribute by sharing our link and subscribing the link. and also contribute if you have any questions or any topic that you would like to share with us. And thank you all and have a wonderful weekend. And we'll see you next Friday at the same time. Thank you.
Thank you.